So, hi all. How many of you happened to hear my talk last year? Yeah, I was just wondering because the start is going to be very similar. So, but hopefully in the second half there will be a lot of new and different things compared to where I was last year. So yeah, I am researching the star known as a yellow hypergiant star with the name V509 Cas. And this research is within the POEMS project. And I also briefly talked about the POEMS project 2 weeks ago, week ago. Time is relative, at the conference here in the observatory as well. So, hello, please. That's enough. Okay, so what we're gonna do in the approximately next 40 minutes, and I will try to hold your attention. We will all have to quickly catch up to stellar evolution to get to understanding what are the yellow hypergiants that I'm studying and why I'm studying these stars in particular, and also why I'm studying this one star in particular, as there are millions, billions, trillions, quadrillions stars in the galaxies. Then I have picked one single star to work on my PhD. So I'm trying to kind of give you an understanding why I'm looking into that specific yellow hypergiant. And also, as we've reached that point and talking about that specific star, I'm also trying to expand the knowledge to not only the properties of that particular star, but also the properties of the environment where the star exists in. So we are finding ourselves at the very top of the Hertzsprung-Russell diagram. So at this area where there is the most massive, most luminous stars, so supergiant and hypergiant stars, and where all the blue supergiants, red supergiants, yellow hypergiants, all of them are located. And to quickly catch up why these stars at the top of the diagram, then the usual stellar evolution that happens is, well, stars in the main sequence, runs out of hydrogen in the core, expands into a red giant, runs out of helium fuel, and then throws out its layers and becomes a white dwarf. So that is the usual evolution of a sun-like star. If we are looking at massive stars, the situation goes a bit more different. So stars with masses more than 8 solar mass or so, or here is a starting mass of 25 solar mass. These stars, when they run out of hydrogen in their cores, they also expand into red giants, but then they finish their lives as supernovae. So instead of this whole big trek across the diagram, they are just kind of moving back and forth at the very, very top of the Hertzsprung-Russell diagram. And these movements at the top here can be quite complicated. So here we are once again looking at the very top of Hertzsprung-Russell diagram. So very high luminosities. The entire temperature range, pretty much. So we find that the red supergiants are at the lower temperatures, and Wolf-Rayet stars, blue supergiants, are at higher temperatures. And here, somewhere in the middle, we find yellow supergiants and yellow hypergiants. So now, for all these stars, we can easily, or not very easily, but we can put them onto the diagram. We can determine their temperatures, we can determine their luminosities, and we can put that point right there. The star is located in that spot of the Hertzsprung-Russell diagram. And then we have to figure out how does the star's evolution work. Because when we start drawing evolutionary tracks, it becomes a mess. So as a star leaves the main sequence, becomes a red supergiant, goes back towards the blue, probably blows up as supernova. But the tracks depend on the initial mass. If a star is very, very massive, it won't even become a red supergiant. And also, if we have this star, we have one observation or a few observations of one star, but the observations have been done in the last 100 years or so, generally. So we have this one blink of an eye in the evolution of a star. And if you pinpoint the star's location on the diagram, there's no possible way to just say that, oh, this star is moving left, or oh, this star is moving right. So, because, well, we don't have enough of a time range, we don't have observations over millions of years to say, oh, this star has moved to the left, or this star has moved to the right. So, to determine if that star that's situated somewhere here in the middle is either moving towards the red or moving towards the blue is very complicated, and there's a lot of nuances to determining that. Hello? Okay. So here we get to the definition of hypergiants. So hypergiants are supergiants, but supergiants are not hypergiants. So hypergiant is kind of this small subclass of supergiant stars. And they generally start with their initial masses about 20 to 40 solar masses. And they are among the most luminous stars. So 1A plus or 1A0 luminosity class generally. And hypergiant stars are quite unstable. So they have large-scale motions in their photospheres, and they have very expansive envelopes. Sometimes they're surrounded by nebulae. So hypergiant stars lose a lot of mass during that stage of evolution. So, for example, we have two stars. We have a yellow supergiant and we have a yellow hypergiant. How do we determine which one is a supergiant, which one is a hypergiant? Generally, you need to do observations for decades or so, because you need to determine the spectral characteristics of the star. You need to see if those kind of large-scale motions exist, what is the variability of the star, and so on. So you cannot just, from one observation, say this one is a hypergiant, this one is a supergiant, because hypergiants are not more luminous than supergiants. They're both very luminous stars, they're both massive stars. And to determine if a star belongs to yellow hypergiant branch instead of supergiant branch, you need to determine this star's evolutionary stage, as yellow hypergiants are in the stage when the star is moving from the bluer part of the diagram, as I showed here. The yellow supergiants are on their way to become red supergiants, but yellow hypergiants are thought to be on their way back from red supergiants. That's kind of this general idea of how to say the difference between them. So we can't just say that, oh, this star is more luminous than the other, it's a hypergiant or a supergiant. So yeah, to determine if a star belongs to the yellow hypergiants, you need to determine the properties of the star spectrum. Okay, so we have narrowed ourselves down in the Hertzsprung-Russell diagram. We are now looking at only this small area of the diagram. So temperatures approximately around 7,000 degrees, although yellow hypergiants can occupy the area right up here. So spectral classes from A to K can be yellow hypergiants. And this kind of area that I grayed out here is known as the yellow evolutionary void. And what that means, I will get into it in a moment. So, this same evolutionary track. And we have plotted some known yellow hypergiant stars here. So this yellow evolutionary void kind of means it's an area of instability in the Hertzsprung-Russell diagram. So there's a couple of those instability regions. This is one of them. And this area kind of became known as the void because in that area of the diagram, there are relatively less stars than in the before and the following evolutionary states. So this area, the yellow void, only exists for the stars that are evolving from red to blue. If a star is evolving from bluer area to the red, so temperature is decreasing, then the star can evolve kind of without any instabilities in the way. The yellow void doesn't exist. The yellow void only appears when the star is evolving towards the blue.
Anni, before you said that we don't know that the star is moving left or right, but I was saying that we are making difference between these two types of stars.
So, exactly. So, yellow hypergiants are thought to be evolving towards the blue. That's the kind of based on last 100 years of observations and determining spectral characteristics, metallicities, and so on. We think they are evolving towards the blue. Yellow supergiants, generally, we think they're revolving towards the red.
But you can distinguish between them by spectra or?
By a long period monitoring of spectral changes, pretty much. If you have like one spectrum or just a few observations, then it's not really possible to distinguish. And there are many stars for them, for those that people are still arguing, oh, is the star evolving one way or the other way? So it's not so clear, but kind of the definition of yellow void is connected to the star evolving from red to blue.
Can I ask one more general or basic question? So the star leaves the main sequence when shell burning of hydrogen begins.
Yeah, so when core hydrogen runs out.
Sorry?
Core hydrogen runs out.
So with motion towards the red, so this is a stage where the hydrogen is burning in shell and the helium is burning in the core. And so the movement back starts when the helium is depleted from the center, or what is the physical state of the star when it starts going back towards blue?
Is the helium running out in the shell? Indra, can you say?
Yeah, of course. This shell hydrogen burning and core helium burning are both working. So this core helium burning starts in the way to the red already.
Yeah, I understand. Yeah.
And it continues when the star turns back. The helium burning in the core continues.
Okay. And when when you have a very massive star, when the helium depletes and another elements, subsequent elements start to burn in the core, and when it gets back, it's already supernova time.
Yeah.
So in a way that when a star becomes a red supergiant star, then it loses a lot of its initial mass. And when it has lost already a lot of mass, but it still has too much mass left, the star starts heating up again. So if it's kind of less than 20 solar masses star, then it will run out of its mass and blow up as a supernova. But if it's still too massive at the red supergiant stage, then it will start heating up again and returning towards the blue. But if it's too massive, then again, it will never reach the red.
It goes to everything is burned out even before.
Yeah. So this is kind of these intermediate stages. And determining, like you can see many bounces here on the diagrams. but you can't really say that the star bounces back and forth and then kind of continues its evolution, because we don't actually know how many times it bounces back and forth here. It could do it a couple of times, it could keep doing it and then blow up as a supernova. So the tracks here are kind of, as a reference, a bit more rough than what the details for specific stars are. But as I said, the yellow void is an instability region. So there are very few stars found in the areas near the void and inside the void as well. And here are a few yellow hypergiant stars. So the dotted lines here show that the stars are variable. So their temperatures over time vary, and at some points the stars can appear inside the yellow void, and then they can kind of bounce back and move out of it. And it is thought that since this area is really quite unstable, that the stars are inside this void for less than 10,000 years only, which is kind of the reason why there are so few stars to be found there. Hello. Okay, so I brought out some kind of 4 points of the parameters for the stars inside the void. So the stars' photospheres have a negative density gradient in parts of it. And turns out that the stellar winds achieve supersonic speeds already inside the photospheres, which means that, well, since all massive stars pulsate, then yellow hypergiants and stars inside the yellow void pulsate at supersonic velocity amplitudes. So, which is thought to be very closely related to the mass loss of the stars. So it is thought that the pulsations are the main driver of mass loss in yellow hypergiants. And since the pulsations are supersonic, the mass losses of yellow hypergiants can be also quite great, so up to like a solar mass or so. And also, there is dynamic instabilities inside the atmospheres of these stars. So kind of the effective gravity of the star's photosphere can be near zero or even a bit negative based on model calculations. And that means that the photosphere of the stars can become detached from its gravitational attraction. So after going through the fact that there are so many instabilities for yellow hypergiants, we only know about, based on the latest kind of count of them in Wikipedia, we only know about 18 of those stars in our galaxy. A few more have been found in the Magellanic Clouds and maybe in a few nearby galaxies as well. And as I said, it is difficult to determine the exact evolutionary stage of these stars. And yellow hypergiants, during the course that we're studying them, have undergone eruptive events of mass loss, which I will go to specifically for V509 Cassiopeia. And yeah, here's a pretty picture. So currently, V509 Cassiopeia has a mass about 11 solar masses. It's thought to have started with around 20 solar masses or so. And it's a binary star, so it has a distant B1 type main sequence companion. And over the time it has been studied, approximately 100 years, a bit more, its brightness has been quite variable, and its temperature similarly has been quite variable, up to like 5,000 Kelvin. And recently that we have been comparing the stars' behavior in the last decade or so and looking at the more historic data, I have found that the behavior of the variability in the star has changed quite a lot in a short amount of time. And we also detect that there are forbidden lines in the spectrum of V509. So it's a pretty cool star. So forbidden lines generally are not very commonly found in cooler stars, and it needs a bit of explanation. Why are they formed in V509 Cassiopeia? So, starting from the oldest data, the star wasn't included in any star catalogs until about 19th century. So it's thought that maybe it was fainter than 6th magnitude, so it wasn't visible by eye, or maybe it wasn't just in an interesting area of the sky, which is quite unlikely. So in the about 100 years, a bit more, the star increased in its magnitude and luminosity by about 1 magnitude. And it was discovered to be a variable star in around 1970s, when larger surveys, or not surveys, but observations were starting to take place. And people were also starting to do time series monitoring of V509. And in 1932, someone measured luminosity about 6.4 magnitudes from photographic plates. But from 1977, we know that the V magnitude of the star was about 5.5 magnitudes.
What's the distance?
The distance is about 5,000 parsecs or so. Okay, here's some data from the 80s, where there's the visual magnitude of V509. There's quite a bit of variability. It's around 5th magnitude, so it's visible by eye. And it looked like the magnitude generally seemed to decrease over time. And here's some of more recent data. So the magnitude has decreased a bit. It has reached about 5.3 magnitudes, but it seems to be stable in the last 10 years or so. So I compiled a bunch of data from different sources here. We have Gaia at the start. We have some data from an observer at the American Variable Stars Association. And this data is smoothed, so it has quite a lot of, the errors are actually quite large for the smoothed data, up to 0.005 magnitudes. So you can think quite large error bars to this data. And then also Tess observed V509 here in a couple of occasions, and we have observations from ALSO's Bright Star monitoring program as well. So they somewhat agree, somewhat don't, but generally, except for that one bit here, they seem to be in a quite good agreement of the variability of the star. So it's amplitude about 0.05 magnitudes. And as I said, it has generally remained very, very stable in the last decade, compared to about a decade of observations here, where it changed by like 0.3, 0.4 magnitudes. Okay, and maybe more informative is looking at the temperature changes in the star. So it is thought that V509 went through a couple of episodes of mass loss in the last century. So first one is thought to have taken place in around 1973 or so, when the star's temperature dropped about 1,000 degrees. And the second one from 1979 to about 1982, when there was another larger drop in temperature. So in both cases, the star kind of ejected its outer layers of matter, and these layers form the cooler pseudo-photosphere around the star. So due to this cooler cloud of matter, we detected that, well, we didn't, but those guys detected that there was a drop in the star's temperature. And as this kind of ejected matter dissipated or floated out to the surrounding environment, then we would be able to measure an increase in temperature again. So in such a way, the temperature has dropped a couple of times in the history. And since the last explosive episode of mass loss, the temperature shot up by quite a lot. So between 1990 and 2000, in approximately 10 years or so, the temperature increased from 5,000 degrees to approximately 8,000 degrees. So about 3,000 degree increase in temperature, so much that at the end of the 90s, the astronomers expected that the star would enter an immediate and more explosive state of mass loss, but that didn't happen. So it turned out that in the beginning of 2000s, the star's temperature seemed to more or less stabilize. This data is mostly also from Teravere, by the way. And some data from the Nordic Optical Telescope, some data from, I think, Netherlands or so. And yeah, the temperature stabilized around 10,900, 10,800 degrees, with a quite large amplitude of fluctuation. So the spread you see here isn't the extent of error bars. This is kind of physical changes in the star's atmosphere. And the temperature is actually fluctuating quite a lot. And now that we picked up the monitoring of V509 Cassiopeia around 2015 here in Delaware again, then comparing those two sets of data seems like the amplitude of temperature fluctuations has decreased, and also that the temperature seems to be more or less stabilizing at around 7,800 degrees. So we'll see what the star is up to next. So this is more of a zooming on the recent data from 2015 to 2023. So here's data from both Teravere and from the Nordic Optical Telescope as well. So, and the similar dates, the data points of two different spectrographs agree quite well. Yeah, okay, but to more or less better understand the changes in the star's photosphere, star's outer layers, it could be more interesting to look at the pulsations of the star. So we measured the radial velocities of V509, and here both in Teravere and also with the Nordic Optical Telescope. And to determine the radial velocities, we used very strong spectral lines in the star spectrum. This is a silicon line, silicon 2. And here's, I brought out a couple of different epochs. So in one case where the radial velocity is small, and in one case when the radial velocity is quite large. So as the star's surface expands and contracts, we see the change in these strong silicon lines. So on one case, the star's surface is more expanding towards us, and in another case, the star's surface, kind of on average, is contracting. So this is silicon line? Come on. But there are more interesting lines than looking at this big, strong silicon line. And one of those is ionized iron line. So these are some spectra from Nordic Optical Telescope, and you can see this line has several different components. So it has an absorption component, and the absorption component should move together with the stellar surface. So as the star expands, as the star contracts, the absorption component's velocity either increases or decreases. But this line also has a couple of emission components in its wings. And to say why the emission components are formed, we would need some kind of nebulosity around the star. So no large-scale nebula has been detected around V509. So therefore, wherever the emissions form, it has to be a smaller scale structure, like a disk. Why it's specifically a disk, I will talk as soon as the remote works. So if the emissions are formed inside from the star's disk, then the radial velocity of the emissions would not change with the pulsations of the stellar surface. The radial velocities will remain the same, and the intensity of the emission components that we see would directly depend on the location of the absorption line. So as the absorption is at higher velocities, then one or the other emission component would be either stronger or weaker. And as the location of the absorption changes, so does the relative intensity of the emission components. And another reason to think that this could be from a disk is a line that is a forbidden ionized calcium. So this sort of emission line has been mostly detected or has been detected in B bracket E stars. So B-type supergiants that have forbidden emission lines in their spectrums. So, and this line in B bracket E stars has been connected to the disk structure of the stars, as B bracket E stars have very extensive, large dust disks around them. Keplerian disks, and calcium, the same calcium line has been noted as one of those indicative lines of these disk structures. And we see the same calcium line here in V509 Cassiopeia spectrum, and also the radial velocity of the calcium line does not change as similarly to the radial velocities of emission components, but this absorption that should come from the stellar surface moves according to the pulsation state. Okay, so as I mentioned, B bracket E stars that are blue massive stars, and the bracket E here means that these stars have forbidden emission lines in their spectrum. So for example, the same forbidden calcium and also forbidden oxygen lines. Both of these lines are thought to be formed in the disk of B bracket E stars. So they have large Keplerian disks around them. There's a nice picture from an artist about these stars. And as there was a previous plot where, can I go back a lot? Should have put it again. So here on the plot, there was a bit hint where I was going. So we have also plotted here B bracket E stars, which are found kind of on the other side of the yellow evolutionary void. So if we would think that those two stars are connected as their interstellar, not interstellar, but their surrounding environments show some similarities, then when a yellow hypergiant could pass through this yellow void, then they could maybe find themselves as a B bracket E supergiant. One of the theories of what the yellow hypergiants could become in their future. Okay. So, and the most recent thing about V509 Cassiopeia that I looked into is the forbidden nitrogen line. So it's another forbidden line, and usually these sort of forbidden nitrogen lines are found in the atmospheres of very hot stars. So we need to kind of determine how does this line that's usually found in hot stars appear in the spectrum of V509, which is a pretty cool star. And well, as you remember, V509 Cassiopeia has a B1 type, a main sequence companion. So that companion kind of offers us a one explanation for the appearance of the forbidden nitrogen line. So as this companion and the yellow hypergiant are in this kind of larger joint envelope, then this companion would excite the nitrogen in the envelope and cause the appearance of these lines. So there has been a bit of previous research into the variability of this forbidden line, and they found that this variability here corresponds to changes in the R band magnitudes of V509. So Scheffer and Lambert figured that the changes in R band magnitudes, so the changes of continuum in R band, this nitrogen line is about 6,800 something angstroms, so it would correspond to R band continuum. The changes in the continuum could cause the changes in the equivalent width of the line. So here are some recent measurements of equivalent width that I did based on our spectrum that we have. And if we correspond to not R band, but we are corresponding it to V band from AUSA. We also see that the V band changes in the luminosity of the star more or less shows similar behavior to the changes in the equivalent width. So the V band and R band are kind of show similar behavior. So if I would plot the V band magnitudes and the R band magnitudes of the star, then I could kind of make a straight line through them. There is some scatter, but the V band and R band really quite well correspond to each other, which gives us a reason to, well, we don't have R band observations for such a long time, so we can kind of use V band instead of R band to look at the possible connections. And yeah, so the changes in the star's continuum could correspond to the changes in the equivalent width that we are seeing. But also it could be corresponding to the companion of V509 Cassiopeia. So kind of how is the companion located in reference to the yellow hypergiant? This could also influence this forbidden nitrogen lines. So this is kind of a bit of a work in progress thing for me right now. But all in all, I hope I kind of caught you up into what are yellow hypergiants, why we're studying them, and why V509 Cassiopeia is specifically quite an interesting star. And we are looking at the changes in effective temperature, the pulsational activity in V509, and more specifically at the forbidden lines in the spectrum of V509. And we think that there could be a disk-like structure around the star, and the forbidden lines that we are seeing in the spectrum could show many similarities to B-bracket E stars. And that's it for me.
Thank you. Questions, comments?
Wondering, is there any prospect at all of studying the envelope or maybe even the disk by interferometry? You wouldn't be able to do anything with VLTI, but maybe COAST in Cambridge. Because it's rather a bright star.
It is a very bright star.
Yes, and as far as latitude goes, close to be well placed.
But very distant.
But it's very.
Well, that is true. That is true. That is true.
So I think to see the disk, it's too small of a structure to
Have
be
you-
seen.
Can you maybe give an estimate in kind of milliarc seconds?
So generally, the V509's even companion has not been separated from the
Ah.
star. So the companion of V509 Cassiopeia is known to exist because there were observations in ultraviolet, and there is a very strong ultraviolet part of spectrum.
The
That-
ultraviolet excess.
Yeah, that corresponds to a B-type companion,
Mhm.
but the two stars have not been.
So no
separate.
lines. It's not a spectral binary.
No, no.
No,
Oh,
you cannot separate the two.
right. And then I guess your argument is, well, a fortiori, if we haven't even got, if we haven't even spectrally, let alone interferometrically discerned the B star, the B companion, then the prospects for studying the disk interferometrically cannot be good. Or indeed the envelope. You've got two things, I guess. There's the disk and the envelope.
Yeah, so the
Both
big
are
envelope
just
kind
too
of,
small, angularly too small.
except for interferometry. Some closer yellow hypergiants have been monitored with interferometry, I think.
Yeah. So this yellow void region, you specifically stated at some point that it's an instability region from red to blue.
Yes.
That's true. So the other way is not.
The other way it's not.
So if you find a star there, it's more likely to be on its way to the red than the other way.
More likely, yeah, but it could be moving the other way. Yes. So you cannot just put a star on the Hertzsprung-Russell diagram. Oh, it's in the yellow void. It's a yellow hypergiant. That doesn't work like that. So
Well, yeah, but you have probabilistically.
you have most yellow stars are yellow supergiants. Some are yellow hypergiants, but usually there's quite a lot of arguing before a star becomes known as a yellow hypergiant.
And physically, what makes the difference? It has to say, let's say, there are two stars at the same point. One goes one way, the other goes the other way. Both have the same luminosity, the temperature, and the difference is just
Yellow hypergiants would have a higher rate of mass loss, more photospheric instabilities, large-scale motions detected, and
in terms of what's burning at the moment, is there a difference?
well, can't really see inside them.
I mean, I'm trying to understand, but like physically, what drives the stability in one case that does not operate in the other case, although they look similar on the face of it?
It's a mass luminosity ratio.
Okay, so
After red supergiant epoch, the star loses
yes,
much of mass.
so mass is the
Yeah, but luminosity remains.
Mhm.
And this ratio between luminosity and mass.
the difference in this ratio
Yes.
is the
Yeah.
single thing that makes
Yeah.
But it does not have a strict correlation of nuclear reactions that are taking place inside.
Yeah, the high luminosity is the reason of instability. When the mass decreases, the more unstable it will be.
I will ask more general question. It's just, if I understand correctly, the number of those stars is very small. So the general question is, why, from the galaxy perspective, we should care about these stars at all?
From galaxy point of view?
From galaxy point of view, are they, what is the role of these type of stars in the evolution of galaxies? Or if we,
So they have a very high rate of mass loss, so probably influence to the surrounding region due to like making a nebula around them in a way. But like in the galaxy point of view, they're kind of just part of the massive stars driving the evolution of the galaxy. Just they have a short span of life, so they explode a supernova and then other stars will form and so on.
okay, they are extremely energetic, they can inject a lot of energy, but there are so few of them, so.
Yeah. Well, are there actually few of them? So if they're just a part of evolutionary stage,
Okay.
then the stars that have reached the blue have gone through the yellow hypergiant stage already before exploding a supernova. So some
So there are
stars
few
that
of them at this very
at this
stage,
specific moment, there are few, but there could be many more stars that have already passed this stage and in that sense influence their surrounding regions in the galaxy. Because like if yellow hypergiant stage only actually lasts less than 10,000 years, then this is such a short time frame that there could be many stars that have already passed it and many stars that are heading towards it.
Another clarification about the companion. Do we know the period of this binary?
So if I tried to look up a period, and in literature there's periods from like 600 days to thousands of days to 600 years. So at some point, actually, there are papers that say the companion of V509 doesn't exist. How? Why?
If it's 600 days, then it's not distant at all.
Then it's not this. Yeah. That's like the
Actually,
period.
there aren't any real observational facts or data which can give even some hints on the period. It seems it's a very wide binary, very wide binary.
So how do you know it's even associated with the time? There could be coincidence, like just coincidence.
In principle, yes.
In
principle, yes. But if we know that these ionized nitrogen forbidden lines cannot be excited by this hypergiant itself, so it's a non-direct hint to say that this is real binary, to have the source of excitation.
So the companion kind of gives us a really nice explanation for the existence of forbidden nitrogen. If you take the companion away, then the forbidden nitrogen, how, why, where did it get there?
Aliens.
Aliens, must be aliens. So like companion's existence, if you put it in the system, it explains some, like not only in forbidden nitrogen, but there were, I think, a couple of other things about the star that are explained by the existence of companion, but there's no direct spectrum or idea of like what does the companion even look like.
How big of a telescope would you need to get the spectrum?
I need a very big ultraviolet telescope specifically, I think.
It was discovered by the famous
UVs or
satellite IUV, some 50 years ago. In the ultraviolet spectrum, this yellow hypergiant doesn't emit enough energy, and then in the spectrum, this hot component comes, its spectrum comes out in the vacuum ultraviolet at between 1,000 and 2,000 angstroms, quite far ultraviolet region. So it was discovered that there is a companion.
And there is actually no instrument that can.
So this spectrum has two maxima. One maximum is from the yellow hypergiant in visual part, and then the next maximum is in ultraviolet from this companion. So it's a spectrum with two maxima.
I'm wondering if there's an instrument right now working that's observing in far ultraviolet. Anyone know?
How do what? HSP, how far it goes.
There is some, but there is no such a good instrument as IUE was, I think.
No. Well, on the Hubble Space Telescope, this STIS
Yeah.
spectrograph or spectrometer can observe in ultraviolet part also. But as far as I know, this option on Hubble Space Telescope is very rarely implemented or how used. So this
So we need to write a proposal for Hubble. Got it.